the trick? Thank you. Good evening, everyone, and a very warm welcome to the South African National Space Agency here in Hermanus. Also, a warm welcome to all of our listeners and watchers online. Tonight, we're very happy to welcome an old friend of SANSA, Professor Anu Ojha. And it's my privilege to introduce him to you tonight. Professor Anu is a member of the UK Space Agency's Executive Committee. His work encompasses leadership of the UK's current 2 billion ESA commitments. ESA is the European Space Agency. It includes international relations, skills and future workforce development, parliamentary affairs, stakeholder relationships, communications, and also advancing space science exploration and satellite applications through his ongoing role in the UK's academic sector. But Anu really is, and since I've known him, a teacher at heart. His true passion lies in what he calls championing space, and that is really what he has done here in South Africa along with SANSA. Previously, in his capacity as establishing member of the UK Space Academy, we have worked together to bring thousands of children the joy of space science and exploration. He's worked with our team for many years, and we are very happy to welcome him back in this new exciting capacity as an executive member of the UK Space Agency. And with that, Anu, I would like to welcome you to the stage to take us on a journey through space.
Thank you very much, Dalian, and thank you, first of all, to SANSA for inviting me here. I'm here leading the UK's delegation for the G20 space meeting next week. But it was really important for me to come a few days early and to spend some time again here with SANSA. So thank you to SANSA for inviting me. Thank you to all of you for giving up your time this evening. And thank you also, I think I'm seeing some familiar faces from some students who many, many years ago I had the privilege of doing just 1 or 2 classes with when they were a little bit younger, and I was a little bit younger as well. So thank you very much, everyone. As Dalian said, I have now joined our government in the United Kingdom, so I am a civil servant, but I have kept my academic role in space exploration science at the University of Leicester. And what I want to talk about for the next 45 minutes is some of the challenges and some of the opportunities that we have when we're thinking about space, especially in the 21st century. And I call this a century of real change for all of us. But to set the scene, I want to first of all think about what do we mean by space? Well, I think we all understand space, but where does space begin? Because it is not thousands of miles away, it is not light years away. Space, from where we are all sitting or standing now, is only 100 kilometers away. That is closer than the distance that I traveled yesterday from Cape Town to Hermanus. So space is incredibly close, 100 kilometers. The problem is, of course, that 100 kilometers, it is upwards. And if we want to get there, when we are fighting against gravity, we are fighting against a force that has controlled the way that life has evolved on Earth for billions of years. And once we are in space, then from a temperature, from an atmospheric pressure, from a radiation point of view, this is far more challenging than anything we find here on the surface of our home planet. So even though we have been doing space for nearly 60 years, in fact 70 years, from 1957, this still pushes our technology to its very limits. And if I could ask just for the front lights down, please. When we do get to that final frontier of space, though, the view is breathtaking. And what I'm now showing you is footage taken from space, from the International Space Station, as we go over the night side of planet Earth. We get this stunning view of city lights showing how wealth and prosperity is spread around the world, even on a time scale of decades. We got this wonderful view of the glow of the atmosphere. We can also see lightning strikes with thunderstorms on Earth, separated by hundreds of kilometers, but connected electromagnetically. And traveling at 8 kilometers a second, we see this stunning view of sunrise 16 times in a day. We're now flying over Cuba. We're above the atmosphere, so we have this incredibly clear view of the heavens and the constellation of Orion. And now flying over the United Kingdom, Paris, Italy. Now flying over Cyprus and the Middle East. And of course, as a physicist, and you will agree with me, we get this stunning view, this living physics lesson of the aurorae, the northern and the southern lights, as Earth's magnetic field funnels the solar wind and it interacts with our upper atmosphere. So when we see images like this, it is no surprise that so many people want to be astronauts. But there is much more to space activities than just being an astronaut. And this slide is my attempt to answer the question, Anu, what do you mean by space stuff? So for me, it's really simple. It's 3 things. It's looking out there, astronomy. It's going out there, exploration, with our humans and our robotic systems. But then there's the side that so many of us forget about, but is so important for our way of life in the 21st century. The satellites that are not looking out there, but they're looking back here to planet Earth. This is the world of satellite applications. And I now want to share with you some of the changes that I have been privileged to see during my lifetime. And I want to start with astronomy. So when we think of astronomy, I think most of us are familiar with telescopes. Here we have an image of a very early telescope. I think that is a rendition of Galileo Galilei looking up in 1600 or thereabouts, so 1610. Much more recently, we've got the South African Large Telescope here in Sutherland. And we don't just have telescopes using visual light, we have radio telescopes when we think about the Square Kilometre Array. And of course, we have our telescopes in space like the Hubble telescope and the James Webb Space Telescope. But what are the advantages that telescopes actually give us? Well, this first view is the obvious one. Magnification, making things look bigger. So on the left we have the constellation of Orion, as you would see it here in the southern hemisphere. I want to point out, not the way that I usually see it, which is the other way around. And what you can see there is of M42, the Orion Nebula, and you can see immediately that telescopes will magnify, you can see more details. But there is something even more important than magnification when it comes to telescopes, and that is about collecting light. Because when we are looking at the world around us, everything that we all see, all of us, it's coming through a tiny window in our eyes. It's going through the pupil, which is maybe 5 or 6 millimeters wide. That is our window to the world. And the problem is the pupil is very, very small. Also, when we see an image, our brain then forgets it. But what a telescope does, it is like a giant light funnel, which is collecting light over a much bigger area, and it's funneling that light into a much smaller area. This means it's collecting more light and it's not forgetting that light. If we put a camera there, it will collect the light and we'll start to see fainter and fainter objects. And to show you how significant this is, go back to the constellation of Orion. This is as I would see it with my eye, but if I have my big light bucket collecting much more light over long periods of time, look at the difference in the level of detail that I can see. This is why we are building large telescopes, both here on Earth and in space. And thinking about space telescopes above the dirty window of our atmosphere, I want to take us back now to 4 Christmases ago, Christmas Day 2021, to show you an impression of the launch of the James Webb Space Telescope, the largest telescope that we have ever sent into space. Now, this is an international collaboration. It was built by NASA and the European Space Agency and the Canadian Space Agency. And what you are seeing is the telescope assembly, which was folded up into the Ariane 5 launch vehicle when it was launched from French Guiana. And it is unfolding. You can see we have a mirror assembly made of hexagonal elements in the bottom left. And then what is unfurling now is a huge sun shield to keep the instrument cool, because this instrument is not a visual instrument, it's looking in the infrared part of the spectrum. And this telescope is not orbiting close to the Earth like Hubble, a few hundred kilometers up. This is orbiting around the sun, keeping track with the Earth, thousands of times further away. Specifically, it is going 1.4 million kilometers away to what we call the Earth-Sun Lagrange 2 point. 4 times further than the moon. Now, JWST took 3 months to get out to that position, and now it's there. It is conducting its observations. And I want to share you some of my favorite images. But before I do, compare the images we get from James Webb compared to Hubble. Many people have heard of the Hubble Space Telescope. So this is the Southern Ring Nebula as Hubble would see it. Look at the extra detail that we are getting from the Webb telescope. So you start to see the advances that we are making with more advanced capabilities with new generations of telescopes. And this is my montage of some of my favorite images. And I want to start middle left. This is called the Carina Nebula. And this is a region of dust and cloud in which new stars, new solar systems are forming. 5 billion years ago, it was out of a cloud like this that our solar system formed. So we have seen effectively the birthplace of stars. Not only that, we've also seen the future fate of our solar system. This is the Southern Ring Nebula. You saw it before. This is what happens when a star about the same size as our sun, maybe a little bit bigger, finishes its lifespan and it puffs off its outer layers to form a planetary nebula. So in 5 billion years, this is the future fate of our system. And it's not only individual stars that Hubble's been looking at, it's been looking at galaxies. This is a collection called Stephan's Quintet. Actually, there are 4 galaxies that are gravitationally linked and 1 galaxy that's much closer. What do I mean by a galaxy? Well, for your examinations, a galaxy is a collection of stars, tick the box. But it's not a collection of 10 stars, or 100 stars, or 1,000 stars, or even 1,000,000 stars. A galaxy is a collection of hundreds of thousands of millions of stars. And the light from these galaxies, they are so far away, the light has taken 210 million years to get here, by our best estimate. We are seeing this not as it was now, but we are seeing it as it was at the dawn of the age of the dinosaurs. But finally, I want to show you this image here. And just to explain the context of this image, imagine that you put a pencil dot on your thumbnail. And you hold your thumbnail like this and you look at the size of the pencil dot. For any astronomers here, the angular size of this image that I'm going to show you is about 1/200th of a degree of arc. That full stop holding up, that is the size of sky that I'm now going to show you for this image. And this is what Webb saw. This is a collection of galaxies called SMACS 0723. And when I look at this, I think to myself, well, I can see about 10,000 dots here. Again, you see evidence of gravitational lensing. But the reason I get excited is when I look closer, each of these dots is not a star. Each of these features is a galaxy. We can see thousands of spiral, of elliptical, of irregular galaxies here. We are looking back in time 11 billion years for some of these images. And this is in a tiny scrap of sky. We see this in different directions. So we now know that there are more stars in the universe than there are grains of grains of sand on all the beaches of planet Earth. This is what we've learned from astronomy. But I now want to move to human exploration. So I was born in 1968 and I am old enough to just about remember the last landings by humans on the moon in December 1972. This particular image is from my favorite mission, which was Apollo 15 in 1971. It's the most beautiful of the landing sites. And the way I think about this, more than 50 years ago, in the 4 magical years between 1968 and 1972, the 24 human beings who went to the moon and the 12 who walked on its surface, they are still, at the moment, the only members of the human race to have directly explored an alien world, because that's what the moon is. Now that was more than 50 years ago, but we've sent spacecraft orbiting the moon for many, many decades. These images were taken only a few years ago. 50 years after the Apollo missions, and at every one of the Apollo landing sites, all 6 of them, we see the footprints. Where they had wheeled vehicles on the last 4 landing missions, 3 of those had rovers with them, we see the tire tracks. Because on the moon, there is virtually no atmosphere. There is virtually no weather. And so these footprints, these tire tracks, they are going to stay there for millions of years. Humanity has left its mark in the universe. And after the 1970s, we changed our focus. Instead of going that vast distance to the moon, we learnt to live in space. To live in space for weeks, for months, or even years at a time. And this, of course, is the era of the International Space Station, humanity's orbiting laboratory in space. This was assembled on more than 35 different space missions. And if you add up all of those modules where the astronauts live, we have a volume about the same as a Boeing 747 airliner. And for the last 24 years, we have had human beings living on board without any break. They stay for 6 months to a year at a time. For the last 24 years, humanity has been an off-world species. Now, whenever we see astronauts, we love seeing them floating around. We have to keep our astronauts healthy. But the main job that astronauts are doing is scientific research in this unique environment, in a way that we cannot do down on the surface of our home planet. This is the European Space Agency's Columbus module. And when astronauts do have spare time as such, this is the place they like to hang out. This is NASA geologist Dr. Jessica Watkins on her first space mission, which was 3 years ago, and she's floating in the control tower of the space station, the European Space Agency's cupola module, having this stunning view looking down on Earth and looking out at the cosmos. Now that's exploration with humans, but what about our robotic explorers? Now, I have loved space for as long as I can remember. But if I have to remember one particular time, it was in 1973. I was 5 years old, and I was given a book, I still have it, on astronomy. And that was it. I was hooked for life. Now, in that book, there was this image. This was the best image that we had when I was a child of Jupiter, the lord of the solar system, the biggest planet in our solar system. Now, when I was a child, I knew that we were going to send spacecraft throughout the solar system. I knew that we were going to get better pictures than this, but I never knew that we would get images that were of the quality that I'm now going to share with you. So this is the Jupiter of my childhood. This is Jupiter as we see it now. These images were taken by NASA's Juno spacecraft that has been orbiting Jupiter for many, many years. And this is a planetary scientist's sort of feverish dream. We are seeing storm systems the size of a province, the size of a country. When we look at the great red spot of Jupiter, we're seeing a storm system the size of the Earth itself. This is an atmosphere thousands of miles thick. And when we look at images like this, although they are beautiful, when I see beauty in an image, that is telling me it is incredibly rich in data. Data that I can analyze that will change my understanding. And it's not only all of the planets in the solar system that we have changed our understanding of, it is also the moons of those planets. Because when I was a child, the moons of Jupiter, the moons of Saturn, the moons of Uranus, the moons of Neptune, they were just points of light in the most powerful telescopes that we had. But we now see them as worlds in their own right. We see them as worlds of fire. This is Io, one of Jupiter's 4 large moons that we call the Galileans. And yes, what you can see at the top is a volcano, a huge volcanic eruption going hundreds of kilometers into space. This is the most volcanic world in our solar system. We have worlds of fire, but we also have worlds of life. We are now going to fly with real images. None of these are simulations. We are riding the NASA European Space Agency Cassini mission, which flew to Saturn, taking 7.5 years to get there, and then spent 13 years orbiting Saturn. We are now riding Cassini as we fly over the tiny ice moon of Enceladus, and now we have this unbelievable view as we're flying underneath the rings of Saturn, rings that are so wide that they would stretch 3/4 of the way from the Earth to the moon if you put them in the inner solar system. And we get astonishing image sets like this. And having seen worlds of fire and worlds of life, of ice, we may well have seen worlds of life. Because absolutely astonishingly, in 2005, when we flew past Enceladus, this tiny frozen ice moon, barely the size of the United Kingdom, we found that underneath the thick outer ice, at minus 180 degrees centigrade, we saw salt water erupting through cracks into space. That told us that underneath the ice there is an ocean of salty, warm, liquid water. This is a world ocean that we can see underneath the ice. And when we flew Cassini through these plumes, we discovered organic molecules. Maybe the building blocks for life. So in the last 20 years, we now know that there are dozens of these water worlds in the outer solar system, and it's changing our views on where life may have started and where we may still find life in our solar system. And finally, I want to talk about satellite applications. I think most of you are familiar with weather satellites, meteorological satellites. Here we've got the spare, the flight spare for Meteosat 7 that's on display at the National Space Centre in the United Kingdom. And next door, you can see this spacecraft, which never flew in space. You can see this spacecraft's twin sister, which is located 36,000 kilometers above the Indian Ocean, looking down on our home planet. And what it is doing, it is monitoring the weather. Specifically, it is monitoring these features that you can see here, cyclones, or you may call them typhoons, or you may call them hurricanes, intense storm systems. It's the information from weather satellites that saves hundreds of thousands of lives every year when we get hurricanes or typhoons or cyclones. Now, if you were riding on Meteosat 7, this is the view you would have. We're having day and we're having night, as you can see here. But if you remember back to your school lessons, you will remember that the human eye can only see a certain range of colours. We call this the visible spectrum. It turns out that there are a whole bunch of light waves that the human eye cannot see, the invisible wavelengths, infrared, ultraviolet, X-rays, gamma rays, microwaves. If we can collect and detect those wavelengths, we will get more understanding. And what I want to show you now is our home planet in the infrared and also in the ultraviolet. And we're going to start by looking at 11 years of data from British instruments that were flying in space, and they were looking down and they were measuring the temperature of our oceans. On the left-hand side, you can see the years going from 1993 to 2004. Here you see the temperature of our oceans. And as we can see here, the United Kingdom is lucky. We get a warm water current called the Gulf Stream that stops us having very cold winters and very hot summers. But as we move south to Antarctica, this astonishes me every time I show it. We can see how in June and July in Antarctic winter, the continent is almost doubling in size because of the ice that's forming. Changing our view to look at South Africa, we can see the Benguela current, the cold water current coming from further south, and we can see the Agulhas current, warm water coming here. This is why in South Africa, the east and the west coasts have such different climatic conditions. In fact, the energy stored in Earth's oceans is a major driver of our weather systems. And if we want to understand climate change, then we need our satellites in space. Climate change is real. And when I think of the 54 different things that we have to measure to establish what is happening to the climate, more than half of these we can only measure using satellites in space. So that is the view from the infrared side, looking at our oceans. What about ultraviolet? On the right-hand side, you are seeing the ozone hole that still forms over Antarctica every year and is repairing itself in a process that has taken 50 years or more. We discovered this hole in 1984 when I was maybe 14 or 15 years old at school. And we discovered why it was the chemicals that we were putting in our aerosol cans and the chemicals we were putting in our fridges. They're called CFCs. They were ripping apart the ozone layer, especially in the southern hemisphere. And this is our natural sunscreen that protects us from ultraviolet light. So we changed the rules about CFCs. We banned their use, but it has taken nearly 50 years for the atmosphere to repair itself. We can only monitor this from space. But we're not just looking at the Earth, we are also using active techniques. So what we can do is we can fire effectively radio waves at the Earth's surface, we can detect how they're reflected, we can time how long it takes, and we can work out the position of Earth's surface. And what you are going to see, or what you are seeing here, is a radar map produced using synthetic aperture radar of Mount Etna. This is a volcano in Italy. And what you are seeing here, these are really small displacements. In other words, this is where the ground is bulging by just a few centimeters upwards, or it is sinking by a few centimeters downwards. Now you may think, why are we showing this? This is a snapshot in 1992, but we're now going to monitor Mount Etna over a period of 10 years. And what you will see is the pulse of the volcano. You can see how the magma chambers underground are causing the structure to start moving upwards, moving downwards in other areas as well. And as the pressure builds up, eventually we get a series of volcanic eruptions, as you can see now, and again, and again. And when we do so, you can see how the entire land is responding and moving because of changes of flow in the magma chambers. We can now use this to predict volcanic eruptions. And when it comes down to natural disasters, floods or earthquakes, we can use satellite imagery as we would see it. We can use what we call synthetic aperture radar to look at where we've got flood water. This type of data is crucial when it comes down to emergencies that happen because of natural disasters, when roads suddenly get destroyed. How do we get our aid to the places where it is needed? Again, using our satellites is absolutely key. And finally, satellites have changed our society, our world, and the way we experience it for each and every one of us. For any of you who've used satellite TV to watch sports football coverage from around the world, or if you've watched entertainment from a different part of the world, that's only been possible because of our telecommunications satellites that we began launching in the 1960s, and they enable us to be connected as a global society in a way that was impossible before the space age. Now this is from satellite TV, but I think most of you have got mobile phones, and many of us, we are used to using apps like Uber, or we're used to using Google Maps. These work because of our navigation satellites, what we call GPS constellations or GNSS systems. If you have used an app which tells you your position, you are using space technology. But it is not just for getting an Uber for going from one place to another. Every single international bank transaction in the world is time-stamped against the atomic clocks on these satellites. All of our electricity national grids are regulated using the time stamps from these satellites. If you switch all of these satellites off, the global economy would grind to a halt very, very quickly. And I have not come here to give you an economics lesson, but this is big business. This shows the amount of money that the satellite industry generates every year. Lots of people say, with all the problems on Earth, why are we spending money on space? Well, if you look at the numbers, space pays for itself many, many times over. And in the United Kingdom, nearly 1/5 of our overall gross domestic product is critically dependent on services from space that we take for granted. And for as long as we've had our civil space program, we've had space for defense purposes, space for national security. I just want to show you a couple of examples. So 10 years ago, a commercial company called Maxar released this image and then this image. These are images of Xinjiang province in China. And what it showed was what was happening that was being denied at the time in terms of the treatment of the Uyghur people. Much more recently, this image is from 3 years ago, following the Russian invasion of Ukraine. The story that came out from Russia was this was not happening. And Maxar, this commercial satellite company, released these images. Oh yes, it is. There it is right now. So what we are seeing now is that space is not just part of our critical national infrastructure, it's not just part of our critical societal infrastructure, it is part of our national security and intelligence infrastructure. Space is not just a nice to have, space is a must have. And I now want to reflect personally, so these views are personal, they're not the views of my government, they're not the views of my university, these are just personal views, on some of the challenges and some of the opportunities that we are facing in space over the next 20 years. It is a very exciting time, and I just want to give my pick of some examples. First of all, we are finding now across the world, more and more countries are getting involved in space activities, not just because of national pride, but because this is so important for their futures economically and in terms of providing for their citizens. But one country in particular has really gone up in its capabilities like this. What you are seeing now is the most advanced space station crewed by astronauts that's currently orbiting the Earth. But this is not the International Space Station, which is nearly 30 years old. This is the China Space Station. The first elements were launched a few years ago. China now has astronauts flying in a continual way on their space station. Their progress has been going up like this, and not just with humans in space. China has, with its first mission to Mars, it was successful. It landed on the surface. It put its rover out in demonstrating quantum capabilities in space. And we're seeing this not just in China, we're seeing this in India, we're seeing this in Japan. I have seen the growth of SANSA's focus for space capabilities in South Africa. This is now giving global opportunities for people interested in space and wanting to be part of this. So that is the first thing. The world of space is changing internationally. For the second challenge and opportunity, I want to show you this data set. This is very, very beautiful. It was produced 8 years ago by NASA Goddard in the United States. And it looks like it's satellite images from space until you look closer. And what you can see is all of the clouds have been digitally subtracted from here. We are using, or we were using, high-performance computing capabilities to take the satellite images, take out the clouds, introduce fluid dynamics modeling, and also introducing data about dust coming off the Sahara. You can see the Atlantic conveyor belt of hurricanes, and also smoke coming off the forest fires and sea salt that happens to be in the lower atmosphere as well. And the reason we can do this is one of the challenges we have. We have so many satellites orbiting the Earth, doing Earth observation, but we have so much data that we use less than 10% of it. We need to have better computational systems. We need to have high-performance computing systems. We need to have more advanced AI techniques. We need more advanced machine learning methodologies if we want to make the most of all the data that we have. So here's the opportunity space. in the world of space, we don't just need physicists like me, we need software engineers. But looking at the business side as well, we need people with a finance training, people with legal training, people with the understanding of how politics work. Space is not just for the physicists. Going back to this whole business of computational techniques, this is a beautiful montage from the European Space Agency showing our measuring of the thickness of the ice in Greenland, which is getting less and less because of climate change. Our measurements of the carbon dioxide levels in our atmosphere going up because of climate change. Of chlorophyll in the oceans, which are helping with photosynthesis and helping remove carbon dioxide from the atmosphere. But the challenge we have is we've got all of these measurements coming from space, but very little of those are going into our climate change modelling. And so what we need to do is we need to bring these worlds together. So we are now exploring what we call digital twins. So total simulations of planet Earth, but incorporating our space data and our climate modelling. And we need to do this much, much faster if we are to meet the challenges of climate change. The challenges that face all of us. No matter if you're living in the United Kingdom, you're living in South Africa, you're living in South America, you're living in Asia. We are one humanity, we are one world, and climate change is real. And the last challenge and opportunity is to do with satellite communications, specifically mega constellations. So thousands of satellites orbiting the Earth, linked up together like Starlink or like OneWeb. Now, the reason they are up there is the promise of these satellites. So this is now a personal opinion. If I look at human history and I think of what do we need to improve the condition of all of us as humans, as a society, to me, it comes down to 5 things. Access to food, access to clean water, access to energy, access to skills, access to data. And at the moment, on planet Earth, there are 3 billion people who do not have access to the internet. And what these mega constellation satellites offer potentially is global connectivity. But there is a problem because space now is getting much more crowded than it ever used to be. And what happens if one of these satellites hits another one? We found out in 2009 when an old Russian satellite that was dead, not working, called Cosmos 2251, accidentally collided with a satellite communication satellite called Iridium 33. Now this was not planned, but when these satellites hit, they were traveling, each one was traveling at 8 kilometers per second. So when they smashed into each other, we produced thousands of pieces of debris. Thousands of pieces of debris that went to different altitudes, that went to different orbital inclinations. So what? Well, at these speeds, a piece of debris this big, the size of a small coin, would have the energy of a car hitting you at nearly 100 kilometers per hour. And when this event happened, some of that debris 15 years later is still in space, and we can still measure it, and we still have to avoid it with our satellites. The problem now is that space is far more crowded, and if we have a collision between satellites, we might end up making the whole of space in low Earth orbit unusable. This is the challenge of space sustainability. And in the remaining time I have, I just want to go back to one of my deep loves and my academic area of interest, which is my professorship is in space exploration systems, and specifically I have been involved in the exploration of the planet Mars. This is my lesson, and I'm just going to go around it very quickly on how our understanding of Mars has changed in hundreds of years. I'm going to do it very quickly. When you look at Mars with a telescope, you can see it's got an atmosphere. You can see it's got polar ice caps. You can see it's got seasons, spring, summer, autumn, winter. You can see it goes on its axis. It's got day and night. A day on Mars is 24.5 hours long. So astronomers used to look at Mars and think, is this a place where life could get started?
But then we sent our first spacecraft to Mars, and we found a very, very different world to what we're expecting. Mars has got an atmosphere. You get dust devils on the surface, but the atmosphere is very, very thin. It is so thin that the only reason it looks like a desert on Earth is because of the sand in the atmosphere. The atmosphere is so thin that if you poured liquid water on the surface, that water would freeze and boil away. You could not survive without a spacesuit on the surface of Mars. Some of the adults may remember when Felix Baumgartner did a stratospheric skydive from nearly 40 kilometers. He had to wear a full spacesuit. That is what the atmospheric pressure is like on Mars. Liquid water cannot exist. We do see frozen lakes. We see huge volcano systems. We see a giant tectonic crack, a little bit like the East African Rift Valley. But this is a world which is incredibly challenging and hostile. But when we look closer, we start to see sedimentary rocks. We see ancient river systems. And what this tells us is that billions of years ago, Mars was not like this. Mars was like this. It was much warmer, it was much wetter, it had a thick atmosphere. So the question is, did life ever get started on Mars? Now, what I brought with me are a couple of samples. I brought a lunar meteorite, and I bought a piece of the planet Mars. I have them here, and so after we finish, during the question and answers, if anybody wants to hold a piece of the moon or hold a piece of the planet Mars, I have got them with you. You may think to yourselves, wow, how did these rocks that I have in here get to Earth? They were not brought back by a spacecraft. They got here because millions of years ago, an asteroid hit the surface of the moon, blasted rocks into space, and some of those rocks fell to Earth. And similarly, for the planet Mars, for the meteorite that I will let you hold, 11 million years ago, this was blasted off the surface of Mars, rocks went into space, and some of them ended up landing on Earth. Now, this is really exciting. You could hold a piece of the moon, and you could hold a piece of the planet Mars. But you may say to yourself, what's this got to do with life? Well, if I have a piece of the planet Mars, I can analyze it using electron microscopes. And with some of the samples, when you analyze them, you get these features here. And there are some astrobiologists who say these features may have been produced by ancient life. Now that is incredibly exciting, but these meteorites have been lying on Earth for hundreds or maybe thousands of years. This could be contamination by Earth life. What we need to do is we need to go to Mars and we need to look for ancient fossils or ancient evidence on the surface of Mars. And that's what we're doing, for example, with NASA's Perseverance rover. Now, I was involved with this mission a few years ago until I joined government in my science role with the European Space Agency. This is going on the surface of Mars, this ancient desert landscape, looking for signs of ancient life. Now, lots of people say to me, how do you get a single rover to get this beautiful selfie? And it's very easy. You basically move your camera to take multiple pictures of yourself and you put those images together. So for any of you who've wondered, how does Perseverance get these wonderful selfies? This is how it does it, by putting together dozens of photographs to get a mosaic. Now, we picked Jezero Crater where it's wandering. This is what Jezero Crater looks like now, but this is what Jezero Crater looked like 4 billion years ago. And right now, Perseverance has been wandering for the last 3 years, going up here, going up towards this ancient river mouth, looking for signs of ancient life. The last point before I conclude, though, is lots of people say to me, with all of the robotic capabilities and technologies, why do we bother sending humans into space? Why not let robots do the job for us? Now, it's true, our robots are fantastic, especially when I look at Perseverance. But my answer to the question is this man. Dr. Jack Schmitt. You remember I said that one of my earliest memories was seeing the last lunar landing? Apollo 17, December 1972. Now, Jack Schmitt was a geologist who was picked by NASA. He became an astronaut, and he became the only scientist to go to the moon on the last lunar mission. And the reason I wanted to pick this example here. Here he is towards the end of his mission in the lunar module on the surface of the moon. The distance that the Perseverance rover covered during its first 18 months of operations on Mars was the distance that Jack Schmitt covered on his final day on the surface of the moon in December 1972. So robots are great, but at the moment, no robotic system has anything like the capability of a trained human observer. This is why humans in space for exploration and for science is so important. And lastly, what about the opportunities here in South Africa? Well, I think there are three things that I want to highlight. First of all, in South Africa, you are in the Southern Hemisphere. And in the Southern Hemisphere, the views you get of the heavens are much better than in the Northern Hemisphere. These are views from the Sutherland Observatory. And you are lucky enough, if you're in the Southern Hemisphere, to have a view looking into the heart of our galaxy. You're looking towards the center, the much brighter, the much more dynamic parts of our Milky Way galaxy. You do get views anything like this in the Northern Hemisphere. So the first advantage you have in Southern Africa is that beautiful view of the eye. The second advantage you have here in South Africa that you can build on is the history of astronomical tradition here, and not just with observatories like the South African Large Telescope, but also with the Square Kilometre Array, with the radio telescope array that's being built here and in Australia and involving the United Kingdom as well. But I think the most important thing that South Africa has going is the ingenuity and the creativity of the next generation. I'm delighted to see so many students here in the audience, because when I think of the world, and I was lucky enough to work with my colleagues a few years ago, and we got some pictures from those times, from 2021, 2022, 2023. What it strikes me is that we are all here in 2025. Okay, all of us. But I am a citizen of the 20th century. I try my best to keep up to date, but really, when I look at the rest of this century, it is not my generation that will create the future. It is your generation looking towards the young people. And when I have seen firsthand the interest, the dynamism, the curiosity that we have, I think there are so many opportunities here in South Africa for you to build upon. And then you've chosen to come here, so I know you're interested in space. Please do seize that moment with our colleagues from SANSA. In conclusion, what have we got coming up? Well, I am really excited because next year, after more than 50 years, we're going to see the first human mission going back to the moon. It's not going to land, it's going to loop around the moon and then come back to Earth. It's called Artemis 2, and this is the crew. 3 United States astronauts and 1 Canadian astronaut. And what you can see here is the spacecraft that will take them. This was an uncrewed test flight that went out to the moon. You can see NASA's involved and the European Space Agency. But why I'm so excited is that when they go back, they will have cameras far better than we had during the Apollo missions. And they will share those images with us. And when they go there, this is how they will see our home planet. This is an image that was taken by a robotic spacecraft, Lunar Reconnaissance Orbiter, looking back at Earth. And this is the detail that these astronauts will see with their own eyes, and they will share with us. And I want to finish on this slide because the most important thing we've learned from all of our studies of the planets, of the universe, I would say, is how very special this planet is. Because we might find evidence of ancient life on Mars. We might find evidence of primitive life in the oceans of Europa or Enceladus or Ganymede. But Earth is different, because this is a place where not only life started billions of years ago, but life thrived. Life spread over the entire surface of our planet. It spread in our oceans. Life on Earth has changed our atmosphere. It's changed our geology. It's changed our ocean. You could detect from another solar system. if I was a visitor to our solar system, I would ignore every single one of the other planets and every single one of the moons. I'd come here to this third rock from the sun. This is a very, very special place. And if we want to protect the environment, if we want to create the opportunities for our societies in the future, then our space capabilities, they are no longer a nice to have, they are an absolute must have. And we need our current and our next generation of space workers to carry on and to push the boundaries of what we can do. So I would like to thank you all for your patience. I have slightly overrun. I'd be delighted to take any questions. And then towards the end, as I say, I will get out my lunar and my Martian meteorites. And if you handle them carefully, then I'm very happy with you holding a piece of the moon and holding a piece of the planet Mars, if you would like. Ladies and gentlemen, all the students here, thank you very much. It has been a real privilege for me to be able to present to you. Thank you very much, everybody. And do we have any questions from the audience? I'm seeing what every teacher dreads, which is hands not going up, but I saw a hand coming up here. Ma'am, your question.
How do you manage the traffic in space?
That is a really good question. Space traffic management. The answer is there's a lot of luck involved. Actually, there's not a lot of luck. The problem is there is no overarching space traffic control that is agreed internationally. So different countries have different frameworks for their responsibilities. So, you know, we have our launch regulations in the United Kingdom that say, look, if you're launching a satellite from the UK, then you are responsible for anything that might happen. And sometimes satellites collide, sometimes bits of rockets end up landing in other countries. So we had, last year, we had an old European rocket, I am ashamed to say, from an Ariane 5 launcher landed in Kenya, and it was half a ton. And some of you may remember this. So monitoring the space environment is really important. We do this with radar techniques. This is called space domain awareness. We do then have information. If there's a little bit of space debris, then sometimes we've had to move the entire space station out of the way, especially when we've had anti-satellite tests. One in particular that happened. I'm not going to name the country involved. You can look that up. But this caused real problems. The challenge is there is no internationally binding sort of agreement that people will come to. So this is the challenge of our times. And for the United Kingdom, a real priority is what we call space sustainability. How can we use space more responsibly? You know, what are we going to do when all these satellites finish their lifetimes and they re-enter the atmosphere? What are we thinking about the contamination from hundreds of rocket launchers? We as a society need to be more environmentally aware, because space is becoming congested, it's becoming competed, it's becoming contested. And what you are talking about is arguably the biggest challenge for the space sector, or one of the biggest challenges. So brilliant question, thank you. I'm sorry I can't give you a more optimistic answer at the moment. I had a question back there, Mike.
Right, I've got a comment and a question. The comment is obviously with the space debris, it's rather easy for any nation to create an enormous problem, because it's only 100 kilometers to get to space. You could set up a missile, explode, and put out a vast cloud of debris which would devastate low Earth orbit. So, and you know, if it's possible one day, it's going to happen, and who's going to police that? That's, I think, the genuine problem that we face here. And then my question is, we know more about the moon and many of our planets than we know about the bottom of our oceans. So are we heading in the direction of developing a technology that will allow us to map the sea floor? I know water's a bit of a problem, but
No, it's a really good point, Mike.
We do really need to know what's down in the oceans, frankly.
Yeah, I mean, I on your first point, I'm glad you said what you did, because it is the challenge of our times. About, as humans, we're really creative, but we can also be really destructive, and that's as far as I'll go. I'm now a civil servant, but I'll be happy to talk offline about some of my thoughts in more detail. But yeah, your point on the oceans is absolutely true. You know, I think, you know, when we look at our Earth should be called planet water. 71%, nearly 3/4 of our planet's surface is covered in water, and the average depth of our oceans is 14,000 feet, so that's what, 4,000 meters. Most of the life on our planet is not on our land surface, it's in our oceans, and the ocean bottoms are unknown territory in many cases. So I believe that this should be much more of a priority, and it is being done by oceanographic entities, but I personally think we should be finding out a lot more. And then, of course, you can speculate when you watch films like this and so on, like who knows what's lurking in the abyssal trenches that we find, as a consequence of plate tectonics, etc. I absolutely agree with you. We have this vast, unexplored world of our oceans here on planet Earth, and we've also got our ocean worlds elsewhere in the solar system. So we are now starting to see some approaches from the submarine community in the academic sense, not in the military sense, and ambitions to study the ocean worlds in the outer solar system. So it's a really good point. Any other questions? You have a question there, sir. Shall we wait for the microphone, or do you want to shout? Oh. I like these microphones. These are brilliant because we can throw them around.
I want to ask, as you said, we have got many satellites around the other worlds, like the others.
Around other planets.
Around
yeah.
other planets. I wanted to ask, did you try to find any life forms in? As you say, there is a life form and freezing, and there is other one also that is like too hot, where we cannot find life forms. Have you tried to find life forms in the Jupiter or in Saturn?
Yeah, that's a really good question. So, first of all, why do we think that it needs to be not too hot or not too cold? Well, it's a consequence of chemistry. Because if the environment is too hot, chemical processes, you may not get the right processes, they may happen too quickly. And similarly, if it's cold, chemical processes are too slow. So what we now know is actually there are a lot of places in the solar system which could be right for life. So you were asking about Jupiter and Saturn. Jupiter and Saturn, there have been some theories that maybe in the atmosphere of Jupiter there might be a layer where life could exist. This was very popular in the 1970s. But really, what we're focusing on is the moons of Jupiter and Saturn, where we know that there are oceans underneath the ice. So there's a moon called Europa, there's a moon called Ganymede, there's the moon Enceladus. In fact, there are many of these ocean worlds. And the reason we are concentrating on oceans is because we know on Earth, when you had oceans, as soon as we had oceans, life got started. Water has got these very strange properties that lots of materials can dissolve in water, and it becomes a really good sort of universal solution in which life, if it has the energy, can get all of the stuff it needs. So we are concentrating on looking within the ocean worlds in the future, with one exception. And the exception is the planet Mars, because we have been sending spacecraft to Mars, orbiting Mars and landing on Mars since 1976. And we have got a spacecraft on the surface and our spacecraft going around the planet looking for whether or not there's any indication of life. And one of the missions I was involved with, Mars Express, that's still orbiting Mars now after 20 years, still returning data, we discovered that something on Mars was producing methane. Now, methane, CH4, it's a very reactive gas. And if you detect methane in an atmosphere, it's either being produced by active geology, so maybe some volcanic activity, or it's being produced by biological activity. Now, the levels we've discovered were too small to tell whether this was being produced geologically or biologically. Curiosity and Perseverance have made similar discoveries. So we are looking for life at the moment. But I cannot say that we have anything that definitively proves that life exists. That does not mean that life is not there, but we have not yet discovered the evidence that proves the case. We are still looking. And whether or not you think life exists depends upon the planetary scientist that you ask. But we need evidence. That's how science works. Have a theory, but get the evidence. Really good question. Any other questions that people have? Sir?
So as both the educator and somebody who worked in organizational space work, if you have to advise a youngster who's setting out and say want to do the law aspects of space, would you say, well, go straight out and do a degree focusing on law and get the law degree and then go out and try and find employment in the space environment, or would you say start broader, get, say, astronomy and some science and languages, and then focus on your law, but have that background? What would be the best base to start off with?
No, it's a really good question about which route do I choose. Do I specialize early or specialize later? I think it depends on the individual. So if I look at my case, so my academic studies, my undergrad and my postgrad was way back in the 1980s. And then I decided I didn't want to go into academia. And I did a few years of expedition climbing, and then I became a high school science teacher for 10, 15 years. And then I came back into academia. But I have colleagues who right from day one, they knew that what they wanted to do was fundamental particle physics, or they wanted to do theoretical physics, or they wanted to do space science. I think it depends on the personality, but what I would say in general is your education, whichever you choose, this is your passport for the future. And very often when you are younger, you are not sure what is the best option. So if I have to say, I would say go broad, learn about yourself and what you want. If you asked an 18-year-old me and a 25-year-old me, I had very different perspectives on what I wanted. So my advice would be get the best qualifications that give you the most opportunities and then decide. Because at the end of the day, the qualifications you have as a passport, they will open all sorts of different doors. And it is never too late to come into the world of space. So where's Dalian? Dalian's at the back, and I think, Dalian, you know, you had a long career in journalism, and then you came into our world maybe, when I first met you 4 years ago? So I think it's never too late for people to come into our world of space, and we need this. Because my personal opinion is, in our world of space sometimes, we just talk to ourselves. So we need to get the external advice, experience, perspectives coming in. I hope I've answered your question okay. Do we have any other questions? If we don't, I will hang around for a while, as we say in the United Kingdom, and I'm happy to take... Sometimes people do not want to ask questions in front of everyone, so if it's okay with colleagues at SANSA, we can hang around for a few minutes. Is that okay? I'm getting a thumbs up. And then, of course, for people, if they want to see the lunar and the Martian meteorites, I can explain all about those. If I could just ask for the lights on up here, just so I can show some of the features of the meteorites. But once again, I would just like to thank you all for giving up your evenings. I hope you found this of interest, and maybe it's given you a different perspective. And if you have got any further questions, I'd be delighted to take them at the front. So thank you again. Thank you to SANSA for inviting me. Thank you for SANSA colleagues for looking after me today in a series of meetings. And thanks to all of you for giving up your time and attending. Thank you very much, everyone.